This lesson is for Chapter 3, Section 1, Quadratic Functions and Models. So if you guys would all get your materials ready and open up your textbook, we're going to be starting on page 242 for this section. All right, with quadratic functions and models, the nice part about this is we have worked with quadratics very recently. We were working with shifting them and plotting them, graphing them, identifying them with Chapter 2. So part of the material that we're going to have with this lesson should be review for us. Quadratic function again is going to be something of the form ax squared plus bx plus c. When we graph those models, they end up looking like parabolas. So polynomial functions in general, they're going to be functions that have many terms to them. Poly means many, and nomial means pieces or numbers. Generally, when we write a polynomial function or a quadratic function or a function that has any kind of algebra expression or equation that has many pieces, we write them in descending exponential order. Degrees refer to the exponents in the function. The highest exponent that you find in a polynomial function is going to be the degree. So for example, if we were looking at an x squared function where you had 3x squared plus 2x plus 4, the highest exponent or highest power in that function is a 2, so the function would have degree of 2. So if we were looking at these functions, if we have f of x is equal to 5, it actually has a degree of 0, because even though we don't see it, technically it has x to the 0 power, which is 1, sitting next to the 5. So the power is a 0, but again, we just don't write that x to the 0 next to a constant when we're showing or looking at functions. The second function, f of x is equal to 3x, is going to have a degree of 1. The third function, you can see that the highest power in that function is a 2, so it has a degree of 2, and it would go on for higher numbers as well. A polynomial with a degree of 2, like we were talking about earlier, is called a quadratic function. The graph will be a parabola. All parabolas are symmetrical. They'll make that bell-shaped or curve shape, and they're going to be split down the center because they're symmetric. That's called the axis of symmetry. All right, so we're going to be finding that axis of symmetry. It passes right through the vertex of the parabola, so it won't be hard for us to identify or to find. Now, one thing about parabolas, they can either open up or they can open down. What determines that is the coefficient in front of the x squared term. Now, many of you are probably going to remember that from years past. If a parabola has a positive coefficient in front of the x squared term, it's going to open up. A parabola with a negative coefficient in front of the x squared will open down. And if you think about our last unit with our reflections, our parent function opened up. Okay, f of x squared opened up. If we put a negative in front of x squared, that reflected it down. All right, so these two statements go right hand in hand with what we already know. So if we were looking at these particular functions, all right, our parent function, of course, they're all going to be quadratic, so we're all going to get parabolas from these. But notice we're going to have fractions or constants, or like 5/2 is a fraction, but it's of a value greater than 1. These are all going to be shrink and stretch situations, correct? All right, so if we're looking at that first one, we know what the parent function looks like. 1/4 of the parent function. Okay, that's going to be one of those vertical shrinks. Instead of putting in a 1, for example, and getting x squared is still 1, okay, so like our parent function, I'm going to draw that in first. Hold on here, folks. My pens aren't aligning. I'm going to do that real quick. Hold on. Bear with me. Sorry. It's kind of important when we're doing our graphs that I actually graph the dots where I want them to be. All right, so let's try those dots again. Our parent function. Okay, so rather than just throwing it on here, I'm trying to be a little bit more exact. But you guys know that the parent function for x squared is going to look like this. Now, if we do 1/4 x squared, we're still going to end up at 0. We haven't shifted off of our vertex. Okay, but now when we plug in 1, squaring that still gives us 1, but now we take 1/4 times it, we're going to get 1/4. Do you see how our dot's going to be here and back here? If we put 2 in and square it, we get 4. 1/4 times 4 is 1. Do you see how we're going to have a shrunk parabola? Okay, so that's the sketch of the first one. The second one, if you notice, it has a fraction of 1/6 plus it has negative 1/6. So that coefficient is negative. So we just talked about the fact that that's going to make it open down. And it matches what we talked about with our last chapter. If there's a negative out in front of the function itself, it's going to reflect down. So again, take a couple of points and plug them in. 0, 0 is still a point. Now if we put in a positive 1, we will end up with negative 1/6. If we put in a negative 1, we will end up with a negative 1/6. And so it comes with then that our parabola for B is going to be a little bit wider, and it's going to point down or open down. All right, let's move on to C. If you take a look at C, our coefficient again is positive. We have 5/2 there. Now is that value between 0 and 1, or is it over 1? Okay, 5/2 is equal to 2.5, so it's definitely over 1. That means we're going to have a stretch situation, a vertical stretch. So being it's positive, we know it's going to open up. It's not going to reflect. So just take a couple of values and put them in again. We have not gone horizontal, so we know we're still starting at the vertex of 0, 0. If I put in a 1, 1 squared is 1. 1 times 5/2 is 2.5. See how it's going to grow much faster? We're stretching it vertical. If you put a 2 in, 2 squared is 4. 4 times 5/2 is 20/2 or 10. So at 2, we're way up here at 10 rather than only at 4. So do you see how it stretches higher inside that parent parabola or that parent function? Okay, so now let's take C there. And the last one. Again, our coefficient of x squared is negative. It's going to flip down. We know that because we already know what putting that negative out in front of our function does. So put my parent function back in. Take a couple of your values then and put it in. What's going to happen with that constant of negative 4? It's going to be another one of those stretches. Put 1 in. 1 squared is 1 times negative 4 is negative 4. And so is negative 1 squared times negative 4. Putting a 2 in, you could do another 2, although it's going to fall off this graph paper. You'd square 2 and have 4 and multiply by negative 4, you'd have negative 16. So it would be way down past here even. So it's going to be very stretched and bend down. Okay, so we've done that kind of stuff before with our last chapter. This is where we're going to get to be new. All right, standard form of a parabola. If a parabola or if a quadratic formula is written in this format, it's very quick to graph. So if you have a parabola given to you, an x squared function given to you in this manner where you either have a 1 or some other number for a in front of that x minus h squared plus k, h, that number inside there along with k, is the vertex of your parabola. If you think about that, h, that's going to be your sideways shift, right? Okay, we learned about that in chapter 2. K is your vertical up or down. So if you put those two together, it makes sense that our parabola is going to start there. So again, it's very connected to last chapter. Now that axis of symmetry that I talked about before, that line of symmetry is going to be the equation x equals h. Okay, you know that if we have an up or down shaped parabola, our axis of symmetry, Okay, so let's just sketch a parabola here. Our axis of symmetry or line of symmetry is going to be that line that cuts it in half. Well, that's going to be a vertical line. So all of our vertical lines are x equals some number. So that's exactly what that's saying right there. X equals h is going to be, you know, if that vertex ended up being 3, 2, the h value is 3, x equals 3 would be our axis of symmetry. Okay? Remember that the number a would represent a vertical stretch or shrink if it exists. Okay? In a lot of our parabola cases, that number is going to just be a 1, and so we won't actually see something there. But if there is a 4 or a 2 or something, we deal with it like we did when we were sketching those previous 4 graphs. Now, to find the standard form, completing the square is necessary in most cases to create that x minus h squared part. So checkpoint problem number 2 at the bottom of 245 has us practicing this. And the one right above it, the example from the book right above it, is having us do that as well. So look through that one and then come with me through this one. So in this particular problem, we definitely see that we have a parabola. We have an x squared function, but we do not have it in standard form. So we are going to attempt to put it into standard form. So first thing that you're going to do is get x squared alone. So I want to factor the 3 off of the x squared term and the x term. Okay, do you see that if we distributed the 3 back through there, we would get right back to the starting point? So we have not changed the value of our function, we've changed the look of our function. And it's getting a little bit closer to what it is that we are looking for. Now, completing the square, you are going to take half of the coefficient of x and then square it. Remember that process? So half of negative 2 is negative 1. Square negative 1, you get positive 1. So we're going to do it like this. If we square negative 1 again, we get positive 1. But if we add 1 somewhere, we have to subtract 1 as well. Bear with me, this is a little different than when we completed the squares before. And then we still had that plus 4 on the outside. Now, I don't want to keep this here. All right, I want to be able to move that somewhere else. I want to move it outside of my parenthesis. Now, what is the value of that digit there, truly, being there's a 3 outside of the parenthesis? That actually is the value negative 3, because it's 3 times that negative 1 that we're looking at right now. So if I pull that chunk out of my parenthesis, I could have this mean the same thing. Now that might take a couple of times through it for us for you guys to truly be able to get your heads around what I just did. Okay, so completing the square happened in this line. Half of negative 2 is negative 1. I squared it, that's positive 1. So I added 1 and subtracted 1 to get that positive 1 inserted into my function. Now, in order to do the factoring piece, I need the minus 1 out of there. I just want to keep the plus 1. Well, when I pull that minus 1 out of the parenthesis, being there's a 3 out front, it's not just a minus 1, it's a 3 times minus 1 that I'm shoving to the end of my expression or my function. Okay, so that's where that next line comes from. Now I'm going to rewrite the x squared minus 2x plus 1 as x minus 1 squared. Okay, that quadratic in there, x squared minus 2x plus 1, would factor into x minus 1 times x minus 1. So I've just rewritten the factored form as an x minus 1 squared. Now we're almost there. So 3x minus 1 squared, combine those two constants, and I have a plus 1. All right, so if I was going to graph or sketch this parabola, I definitely see that my vertex, okay, here's H, here's K. My H is 1, my K is 1. Here's your vertex. So we'd be able to go over here and we'd be able to graph the point 1, 1. Okay? Now, as far as coming up with additional values, okay, you see that there's a 3 out front of your parent function. So this parabola is going to have a vertical stretch placed on it as well. But to come up with those other points, just pick more numbers. Okay, if I put 0 in, for example, 0 minus 1 is negative 1. Square it, you get 1, times my 3 now is 3, plus 1 is 4. So if you put 0 in, you're going to get 4. Now, being this is a parabola, the same exact thing should happen if we put in a 2. Okay? And you could pick some more numbers as well, or just know that this is going to shoot up, stretched, and skinny. All right, let's do another one. Sketch this graph and identify the vertex and the x-intercepts of the graph. So watch for problems in your homework that have multiple pieces to them. So first of all, this is not in standard form. Okay, it's in ax squared plus bx plus c form. So we're going to change that first. So let's do one of these things again, where we're going to take half of this, half of that's negative 2, square it, which is 4. We want to get a 4 onto this much of our function. So I'm going to add 4, but in the same breath I'm going to subtract 4. Okay, that way technically I've added 0 to it. Okay, now group up so that you can factor this part. Okay, so for just that part, we can factor that into x minus 2 and x minus 2, correct? Okay, there was no number outside here, up in front, this time. So that value of negative 4 is still just a negative 4. I can combine that with my positive 3 on the outside, and I have a minus 1. Now rewrite the x minus 2 as an x minus 2 squared. Do you see how we've just gotten us into standard form? H is 2. K is negative 1. So my vertex is 2, negative 1. My axis of symmetry is the x equals h line. Well, if h is 2, my axis is going to be x equals 2. Okay, so now let's graph this. My vertex is 2, negative 1. So a couple of more points for us. Plug in a 1. Okay, so if we put in 1, we're going to have 1 minus 2 minus 1. Okay, so negative 1 squared is 1 minus 1. We're going to get a 0 when we plug a 1 in. So when you plug a 3 in, you should get a 0 as well. Okay, if you plug 2 in, we're going to get 0 minus 1, or negative 1. Oh, we had 2 negative 1. Sorry, I got to go to 4. I need to put a 4 in. Nix that. 4 minus 2, square it, minus 1. Now 2 squared minus 1 gives us 3. All right, so when we put 4 in, we're going to get 3. And if you put 0 in, you're going to get the same thing. Okay? Now, parabola. Go ahead and connect them. X-intercepts. Okay, we found them when we graphed our sketch. Here's one. Here's one. So our intercepts, we have the point 1, 0, and we ended up with the point 3, 0. And we've got all our stuff. Now, if they give you that information and ask you to write the equation of the parabola, all right, so you're going to be given the vertex rather than find it, or you're going to be given an xy point that's on the parabola. Okay, that information can be used to work that last kind of problem we were doing backwards. So remember that in standard form, hk is your vertex. Remember that f of x is the same as y, and then the x that in there is still just x like always. So you're going to have all of that information except for the value a. If there happens to be a stretch or shrink number, you're not going to get that one. That's the one that we're going to solve for, and then we're able to write our equation, putting all of that stuff back in. So let's do this one a practice. Write a standard formative equation for a parabola with vertex of negative 4, 11 and passing through the point negative 6, 15. So if we're looking to write a parabola function in this form, we already have h, k, negative 6 is our x value, and this is our y value, or f of x, right? So when you're looking back over here now at the stuff that we need to fill in, we have almost all of it. So f of x, 15. We never got anything for a. X is negative 6. H is negative 4. And k is 11. So simplify. Now negative 6 times negative 4, whoops, x minus h, sorry, back up the train. When you're putting in x minus h and it's a negative 4, remember that's a minus, so I missed that. We're going to get negative 2 in there. So 15 equals 4a. Negative 2 squared is 4 plus 11. Move your 11 over. And now divide both sides by 4, and we get 1 for our a. So we're not going to have a shift or a stretch or shrink on this one. A is going to be a 1, so we won't even really see it. So let's put our function together. F of x, therefore, is equal to 1, which we're not going to write, x plus 4 squared plus 11. And there we are. Okay, so all that plugging in and solving was to determine whether or not we were going to have a value out in front of that parent function parenthesis or not. Now here, this is something I was talking about with you guys briefly today. When a vertex isn't given, remember there's another way to find parts of the vertex. The x value of the vertex can always be found by taking negative b over 2a. So if you have a function something like this, I just made that up. A, b, and c are those numerical values in the function, right? So in this particular one, a is 3, b is negative 1, and c is 6. So if we were going to try to find the vertex of that function, or of that parabola, we would take negative b over 2a to find the x part. So negative b would be 1 over 2a would be 2 times 3, or 6. Now to find the rest of the vertex, you would have to plug this in for the x in the function. And you're going to solve then for the f of x or the y to go with it. Okay, so we'll be doing that in our next problem, so I'm not going to finish that part out for now. So negative b over 2a is another option to get half of your vertex. That will give you the x value. You can plug that in then to your function to find the y, and then you have your vertex. All right, so this one is one of the application problems that you're going to be seeing in the homework. So this one happens to be checkpoint problem number 5, page 247. We're going to find the maximum height of a baseball given the following function. Now, maximum height of the baseball. Think about throwing a baseball. When you throw it and launch it, it's going to go a certain distance, right? And it's going to have a certain height before it starts falling back down. The highest point of the baseball would be the vertex of the parabola, right? Okay, so think about that when you're making this thing. If we're looking at this particular one, I'm going to use, instead of trying to complete the square on something like this one, I'm going to use the negative b over 2a to find my vertex, because that's what I'm shooting to find to get that maximum height of my ball. So negative b over 2a. b for this function is a 1, so negative 1 over 2 times negative 0.007, which is a. So we're going to have negative 1 over negative 0.014, and if you punch that into your calculator, you're going to get 71.4. Now you're not done. Remember, this is your x value. The height that we're looking for that our ball got, that's the y value, because that's the, we right now have the x value. We have the across. If we're looking for the height of the ball, we need to know how far up that arc it got. So take your x value and plug it in. So negative 0.007 times 71.4 squared plus 71.4 plus 4. Plug that x value in, and now we're going to solve for y. So doing 71.4 squared times negative 0.007, you get negative 35.7. And then plus 71.4 plus 4, and all of that together gives us 39.7 feet. Okay, so that kind of problem, not so bad. All right, here we go. For tomorrow, I would like these 5 problems, 22, 38, 44, 48, and 58. But do lots more, especially where you're having to do that complete the square type step. Those in particular, let me see if I can hone you in on that section again. Mostly those problems are going to be found, I believe, in 17 through 34. Okay, so work those. Make sure that you can get comfortable with that, and if you can't, come back to class, and that's what we need to work on. All right, so that's it for today. We'll see you guys in class tomorrow.